Dear students, today I am starting another topic, Fft, that is fast Fourier transform. What is the purpose of, as the term suggests, fast Fourier transform means to solve the problem with much less mathematical complexities. So let us see. So to start with, for DFT, we need the number of additions is equal to solve endpoint problem, endpoint sample. We need to have number of additions is equal to n into n minus 1 and multiplications n square. But using FFT, it is reduced much less. That is, the number of additions required is n log base 2n and multiplications is equal to n by 2 log base 2n. So let me take an example. Suppose I am having a to solve a problem where capital N is equal to 512, means number of samples is equal to 512. Using DFT, the number of additions required is equal to n into n minus 1, that is 512 into 512 minus 1, that equal to 261,632 number of additions you need to perform, and multiplications is equal to n square, that is 512 square, that is 2,62,144 number of multiplications you will have to perform. Using FFT, you see n the number of additions required is equal to n log base 2n, that is 512 log base 2 512, that is equal to 512 into 9, that is 4608 number of additions. And using for multiplication the same logic, that is n by 2 log base 2n, the number of multiplications required is 2304, that is 2304 number of multiplications you need to perform for a 512 point sample. So percentage savings in addition, that is 100 minus using FFT number of additions using DFT number of additions, here it is given, and the percentage is 98.2. Similarly, using multiplication, it can be shown that the number of calculations required is equal to the percentage savings is 99.1%. So that's a huge amount. So how do we solve such complex problems? Look, for DFT, first I draw the Tweedle factor chart. Since I have taken a 2 point, you see that W20 is plus 1, W21 is minus 1, like W22 will be plus 1, W23 will be minus 1, and this will continue. This cycle will continue, and I have already discussed how to calculate the Tweedle factor in the previous lectures. So using DFT, the expression is given by this one. So let me take a 2 point DFT. The computations are given. You see, so here it comes this one, here it comes this one. So the expression reduces to this one. I remove the W20 because I know already W20 is equal to 1. Similarly, the second step, you see, I have computed I have used the same concept, but here I have taken minus, since W21 is equal to minus 1. So when I finally come down using DFT, the solution becomes 20, and the expressions can be reduced to this form. Look, x0 is given by this one and x1 is given by this one. FFT is nothing but a signal flow graph. Look how I have presented it. Look, if you look at the basic expression, it is nothing but summation and the multiplication and summation. So this part, if you break it into two parts, see, this part is the multiplication part and this part is the summation part. So this equation can be represented graphically, these two equations can be represented graphically in this manner. Look, x0 is equal to x0, here it is x0 again multiplied by 1 x0, here it is x1 into W20, that is x1 W20 over here, and it comes over here. This part is the multiplication part and this part is the addition part. So this expression can be represented in this graph. Similarly, the same thing I have done for this path as well. So using DFT, the computation results were 2-0, and here of also using FFT you get the result 2-0. I think it's quite clear to you right now. Follow this theory, follow this lecture, and tomorrow I'll start with more, even with 4 point and 8 point FFT. Thank you.